Splendid. In that case, talking about something that I didn't realise existed, life beyond binary, please give a warm welcome to Will Cubby.
Hi everyone. Amplified? Yes? No? Yes?
Yes.
All working? Cool. Yeah. Let's talk about. Sorry, I don't know how that got in there. Let's talk about cellular automata. So, for those not familiar, you start with a row of cells. These cells can either be dead or alive. In this particular case, the alive ones are represented by a black square, and the dead ones are the white squares. And we have this rule set at the bottom that defines kind of how these cells behave. So if we want to generate the next iteration of this kind of environment, we use that mapping table, and we get this. And if we do that a few more times, then eventually we start getting patterns. And there are lots of different mapping tables or rule sets that you can come up with, so we need a notation for them. So we just put binary digits underneath the values there, turn it into decimal. That's rule 30. That's one of the more famous ones. And you'll start to find other areas of mathematics showing up in these patterns as well. So rule 18, for example, very nice Sierpinski triangle. And it shows up elsewhere as well. You may have seen the new Cambridge train station has got rule 135. James did a very good video, go watch it. So if that's new to you, awesome, you've learned something new. If you've seen this all before, just wait. You ain't seen nothing yet. So we want to kind of explore beyond binary. Binary's boring. We've done that before. How do we expand beyond binary? How about ternary? So already our rule sets start to get somewhat exponentially more complicated. Instead of a 8-digit binary number, we now have a 27-digit ternary number, which changes the number of possible rule sets from 256 to about 7.5 trillion. And it just gets worse as you go up. So this particular rule set, you get this somewhat chaotic pattern like this. I can still see kind of bits of Sierpinski in there, but whatever. And something I noticed when I was researching this is I found a lot of places where people were rendering binary rule sets, but they would have a different color for when a cell came to life. So essentially it was a 3-color system, and I thought, well, couldn't we just implement that in a ternary rule set? So it would look something like this. This is rule 30, with when a cell comes to life, it's blue instead of black. That's the ternary rule set for that. Turns out you can actually encode that logic into that rule set. And that got me thinking, can we maybe encode other pieces of logic into these rule sets? So here's one I came up with, and see if you can spot what it's doing. So it's shuffling all of the zeros over to the left, and it's shuffling all of the ones over to the right, and then the 2s are acting as walls down the sides. Well, that's just a sorting algorithm, isn't it? We've built a sorting algorithm for binary. So I have a question for you all. We've created a binary sorting algorithm in a ternary rule set. Can we do that? Can we do 3-state sorting in base 4? I don't actually know. If you can, what about the generalized case? Is that doable too? This is not approved by MathsJam. I genuinely don't know. I've not figured it out, and I figured you're the best audience to ask. So let's go back to binary for a second. How else can we move beyond binary without just adding another value? What if we add infinitely many values and have it be the probability of being alive? Essentially, that's kind of what the automata is already, but if we bring in this sliding scale, it gets interesting. So let's look at an example. Let's say this is our input state. We've got a dead cell and then 2 cells which have 50% probability of being alive. These are the possible states that could be, right? And they've all got equal probability of a quarter. So if we check our rule set, let's take rule 30 in this case, add to these 4, you'll see 3 of them output alive and 1 of them outputs dead. So we average those together and we get 3/4 as our output state. And then obviously that will kind of feed back, and that will bias how the next row evolves and so on. So let's run this on a few rules and see what we get. So we get a very nice pattern from rule 14. We get these kind of wobbly lines, which I thought was quite nice. If we look at rule 95, this one stabilizes quite quickly into vertical and horizontal lines, quite cool. Our favourite rule, Rule 30, unfortunately descends very quickly into complete uncertainty. It's that chaotic. But my absolute favourite, I found kind of a family of rule sets that produce a very, very pretty pattern. So I've scaled it down a little bit for this. Isn't that beautiful? Simple rule set producing this awesome, awesome result. And of course, there's one last thing. You can, of course, ternary probability with barycentric coordinates, and you can scale that up to base n. That's all I got. Thanks.
Thank you, Will. My favourite extension there of proof by MathsJam is thesis by MathsJam. If you don't know how to solve it, just hopefully here's someone will.